this added complexity worth the performance, you know? And it's something that we all, as a team, kind of need to just always have in our heads. Team effort is another pretty, basic one that is pretty self-explanatory, but can't hurt to bring it up. So one person can't build a car. I can tell you that from experience. I tried, and it's going to kill you. And we're all doing other stuff. We all hopefully have friends. We want to hang out with them outside of this wonderful organization. And we all have classes. We're all trying to graduate. And I want all of you to be successful, moving forward. And I've only had to do it twice, but if you can't balance it, then we sit down, we talk, and you're no longer a part of FSAE. If you can't balance the load, you really need to, be realistic with how much time you can put into it. Be honest with everyone, because the thing that really hurts us is when someone's like, "Yeah, I can do that," and then they don't do it, and then they just disappear. So it's much, it's frustrating for us when you're like, "I can't do this, I don't have time, I'm struggling in my classes," but it's much better to do that and be honest with us, and we respect it a lot more than if you say like, "Oh, I can do that," and just don't show up for months. So obviously split the work, just be honest. We are a team and we succeed as a team. Realistic timelines is another one. So this one's hard, especially because there's so much going on. You get like, Richard doesn't order your part in time, then you're set back by a week, or the wrong part comes and then you have to reorder it, or stuff like that. Something breaks, you have to remanufacture something. Random Sundar projects pop out of nowhere, and then your whole month is gone. And you just need to be realistic, and you need to set hard goals, push to meet those goals. Plan out everything to stay on track. So whatever you need to do to remember and allocate your time correctly. Some people use planners, Google calendars, whatever it is. You just need to stay organized. And always plan for the worst case. If shipping says it could be here in like 2 to 3 weeks, plan for 3. If you get it done early, no one's going to be like, "Why'd you do that early?" But really, this just keeps teams realistic from being overambitious, and really puts things in perspective. So, if you're like, "Oh, if I just had one more week, these uprights could be so much better," then maybe it's not worth it. So a big one, especially because so much of the leadership is leaving, is iterative design. So we've already done a lot of the heavy lifting as a team for 4 years, and when we leave, we don't want you guys to start from ground zero and design a whole car from scratch. We have stuff, some of it works, some of it doesn't, and you guys should focus on the stuff that doesn't work, so it all somewhat works. Get it, all working good, and then go and try some ambitious ideas. So there's a lot of teams, a lot of specific things I can think of that just we're behind in, we're lacking. Suspension. No one even has scratched the surface on tires. When we get to the technical aspects, you can see that is where everything starts. So we're not even at a point as a team to go through and design this car in the right process, because we don't have enough knowledge. So before we go out and try, switching out every aluminum component to magnesium, let's Like there's a lot to be done elsewhere. So like an example of like a iterative design, I'll use the shifter. So we've used mechanical shifter. The step up from that would be just replacing the mechanical aspect with the pneumatic aspect. So you have an up and down lever, you just have an up and a down button. So it's not like this huge jump. It's step by step. And then after you get the pneumatic shifter working well, then you can program logic into it. So if you're in this gear, the shift is different, or even automated shifting. So just once you hit a certain RPM, it'll auto shift for you. So like that would be the progression. And skipping that middle step adds so much extra complexity into it. You don't even know if the pneumatic part's going to work, let alone all the logic to go with it. So you really just need to go in steps. Make sure where you're at is working well before you move up. Yeah, definitely. Again, this just helps with scope creep and over-ambition. If you take baby steps, they're not that bad. But if you try to jump like 4 stairs and you slip, you're falling all the way down. And the last one is business case. This one is going to be for like tackling team disputes. So a business case document is pretty much a document that just lists out specific and measurable effects of your decision on performance, if it's cheaper, if it's faster, more reliable, whatever the case is. And this is something you see like when you go into industry. If you go to your boss and you say, I want a new computer, he's going to be like, no, it costs money, get out of my office, you're wasting my time. But if you give them like, if I got a new computer, I'd be this much more productive, this would save the company this, it comes out in the green, then any good manager is going to make that decision. So I mean, ultimately, the team lead has a final say in any decision. So if you come up the next year, Tim's going to be team lead, and you say, I'm going to do this. Tim says, I don't think that's a good idea. And you bring him a business case, and it's outlined, and he agrees with all the assumptions you've made, all the numbers, and it comes out your idea is better, then a good team lead would, say like, yeah, let's do that. But it really, you don't want to again, you want to, sometimes you have to go with just good enough. You don't want to just keep designing. You don't want to keep adding functions and features, because eventually we have to go to competition. So this is really good, unbiased way to, solve disputes. Really, if your idea isn't going to convince the team lead, it's not going to convince the judge at competition. Ben will attest, these people know way more about anything you think you know about on this car.
There's no way you're going to BS this. You're not going to BS your intake to the guy who designed the turbocharger for the Ford Ranger. Or not Ford Ranger, Ford Raptor.
Don't understand is like, even if your car is not the best to win design, you just have to have the best reason behind all of your decisions. So, even if your car is not the fastest, not the cheapest, not the most advanced, if you have good, solid engineering, business, practical reasons behind your decisions, you'll get full points for those decisions. And pretty much in this all these kind of documents go together. So the functional spec, the test case, document, and the business case all go together. So you pretty much have to prove that your idea is worth doing and not the other way around. It's not like Tim is going to have to go through and do a business case on why we shouldn't do things. So if you're really adamant about your idea, this is my recommendation for handling disputes. And make sure the team just moves forward as a whole. There's no hurt feelings, because that can kill teams. Okay, so now we'll actually get to the car. I'm sure you guys are bored of me talking about random and abstract stuff. So I'm going to kind of go through this in level of like priority. Before I do, I want to kind of mention that big things, especially on the electric vehicle, like battery pack, motors, all of these are kind of like outside of this hierarchy, right? We do design those, but other teams buy them. So we have more freedom than most teams, but those for now should kind of be treated as bought parts. Things we can't change, and things that kind of just come with the competition. So for IC Car, like, we're not modifying the block and the mounting points for the engine. Those are something that are set. We should really treat battery pack and the electric motors the same. I'm going to try to keep this kind of general, but I just want to make that note because those aren't in the hierarchy, because those should be done before all this kind of happens. You just kind of want to import them in. So the first one we're going to get into is tires and car dimensions. So the way you start designing any car is you place the tires where they need to go. So you're going to determine, based on track size, turn radius, and things like that in the rules, you're going to determine how big you want your wheelbase to be, pretty much. From there, the first thing to do is consider, go through, find all the tires that kind of suit the size you're thinking of. We have access to tire data, and this in itself is a rabbit hole that no one fully grasps how deep it is. There are teams who have PhD students doing their dissertations on small parts of the tire data. This is stuff that there's no real analytical formulas that describe rubber and how it reacts. And it's so complex that understanding tire data is probably harder than designing the whole rest of the car. Truly and honestly. There is one team who makes their own tires, and their advisor is the lead researcher in tire analysis, and it's absolutely insane. It would probably be easier to design your own internal combustion engine for this competition than to design tires for this competition. So when you do this, you need to make some assumptions about what your size is going to be, kind of like where your CG height is going to be, your weight and your weight distribution. And to make these assumptions, you're going to probably pull off old cars. So first car is kind of shot in the dark. Now that we have some cars built, it's a lot easier. But from the tires, you get pretty much, if you know how to work with it, you can get, very detailed what you want for your static camber, what you want for your camber gain, cast or toe, PSI, what you want your weight distribution to be, what you want your slip angles to be, and that goes with steering, what you want your Ekman to be. And really, if you think about it, all forces coming into the car, so not things that motors are in the car, go through the tires. So this is where it all starts. All force that go into the car, neglecting aerodynamics and things like that come from the tires. So this is where a good team starts. And you can see, we'll get into, once we get into suspension, not knowing any of these makes the, designing suspension really hard, because you have to guess what are good numbers for all of these. Next. The next thing you should do after deciding like the size of your car and the stuff tire data gives you is to put in all the stuff that's not changing. So again, these are like motors, battery pack, motor controllers, the driver, high voltage wire, like differential, axles, pedals, rack and pinion. These kind of like sub-assemblies that are almost independent of the rest of the car go in. This is going to make sure you have a good space. The big one that our team kind of has suffered on is the driver, definitely. 15 car fit the driver really well, but was really big and no one knew what we were doing, so it didn't go around corners. IC car is too small, so anyone like a millimeter taller than Tim does not fit comfortably. EV car is like way too big, and like anyone shorter than Zach doesn't fit comfortably. So we really need to like go and find this middle ground. And, we have a really nice 3D model of a person with 95th percentile. You can move all its limbs. His name is Percy, and I think that if we put that in the model before we start designing a lot of these other systems, it'll really help us get a more comfortable and drivable car. And we can go on from here. The next one that gets priority is suspension, steering linkage. This one is special because it comes directly from the data you get from the tires. And it's not, it can be very complex, but it's not as bad when you have all the values you're trying to hit. So if you have a list of, I want this roll response, this camber gain, all of this, then you have a benchmark to try to hit. Suspension has been so hard for us because we just guess on a lot of these numbers, or we run it through like a simulation software and say, looks okay, model it, all works. We like move the wheel up and down, and you're like, that works, right? Like, so that's why suspension has been so hard in the past. So specifically about suspension is, all the tire data, where you want all those values, you pretty much just make your control arms to match. From there, you need to interpret the spring rate curves from the shocks and make sure that we're going to get a good progressive spring rate. We don't want to be bottoming out, and we want to make sure when we design the suspension linkage, the belt cranks, that it suits the shocks correctly. From there, you pretty much have your suspension, and it's defined off of values from the tire. So something specifically about suspension is that this is one area you don't want to go nuts with on weight savings. Even if it doesn't break, if it moves, you're going to get a lot of diminishing results in performance, right? So if you, especially if you have the right values, like my tire wants to be at this camper with this weight on it, if your tolerances aren't good or your things are bending, then you're not hitting those numbers and you're not getting your performance out of it. So you want to make sure there's as little compliance in the system as possible. And suspension is arguably the biggest, performance aspect of the car. If you have like a super badass engine, really bad suspension, your car is not gonna drive well. So just look at American cars. I don't like them. So real good teams will use a vehicle simulation software, and they'll simulate the whole car going around the track. So this is kind of where we want to go to. And you can find old tracks online, like old endurance tracks, put those in, put your car around it, and you can see the response your suspension gets at every single point. And this is really going to help you design suspension for this competition. Parts, especially because we're doing so few numbers, like the setup time for machining a part is like the majority of like the work that goes into it. So if you can set it up once and have it, the whole upright with the control arm mounts and the, tie rod adapter all integrated in one, that might be better than designing or like machining like 6 different parts that all bolt together. Another one is accuracy. So again, you want to minimize compliance, you want to maintain accuracy, and you want to make sure that you don't have slop. If you have too much slop in your steering system, you're actually disqualified from competition. So this is serious, and you don't want any, especially with some of these suspension components, you don't want things to kind of like get out of line because of bad tolerances and start bending things. So kind of rule of thumb, all points that connect to the chassis must be at nodes on the chassis. So where your control arms mount, you can be at a node. Where your shock mounts, at a node. Where your belt crane pivots, at a node. And this is going to help you get the least compliance.
For those who don't know, can you define nodes?
Yeah, so a node on the chassis is basically where 3 or more bars meet. So I think there's like 37 nodes on our chassis. And really, these nodes are the key. So when you do any force analysis on tubular structures, you just do it based on the nodes, not so much on like the shape. So this is kind of a diagram of suspension. As you can see, it kind of gets real complex. This is just talking about instant centers, which are basically where the car pivots about when you're turning. And so again, if you don't have all those values that you need to find, you start looking at this and you just have to start guessing numbers. So it's really why tires are important. Next, we're going to get into ergonomics. This has been our weak point, kind of, at least for the past 2 cars. So again, if we use PERSI, we put PERSI in the assembly and determine a real accurate, like comfortable driving position. So do we want them at like really laid back? Do we want them like kind of upright? This is all decisions you guys need to make based on kind of like testing it out. Grab a chair, kind of say like, oh, this feels good. But if you guys can get, look at the past cars and say like, this was too upright, this was too laid down, this was pretty good, and kind of narrow in to where you want it. That's going to help in design a lot. And from there, you're going to try to place everything and design everything that interacts with the driver. So this can be pedals, seat, steering wheel, headrest, kind of stuff. And then the other thing you're going to do is probably at this point is the firewall. So it's really important to keep the driver safe. And if your firewall, especially for the electric car, is not up to the rules, you're disqualified. So it's important, and you don't want to not account for it and kind of get stuck later on in the design process. After that, uprights and hubs. So a lot of people, I feel, think that the uprights and hubs are like super complex parts, and in a way they are, but if the design process is done right, they're really just connecting points that already exist. So this year, the suspension wasn't well defined, so it made designing the uprights difficult. Zach would come to me and be like, you know, what's this? And I'm like, if it's not in the points for the suspension, you're kind of fucked. And it's difficult because especially for the electric vehicle, because we have the gearbox integrated into our upright. You know, the suspension and uprights are two different teams, but you know they interact with each other so closely that if the suspension team does not give points to the uprights, you know, you can't go through and design it. So really, the job of the uprights and the hubs is to connect the vehicle to the wheels. That's what it does in the simplest term. You know, it kind of sounds easy, but there's, you know, with so many constraints, you have to be very creative, but at the same point, you know exactly, you know, where everything needs to go. So using where the wheels sit, the control arms, steering points, and any other components, you just connect the dots. And the other thing is, depending on how your suspension needs to be adjusted, you might have to account for that as well. And then after that, it's pretty much free-for-all for almost everything else in the car but the chassis. So everything else should be designed and should be put in the full assembly. Everything should have mounting and fasteners. And at this point, all your systems are starting to get connected and your designs are going to change. And eventually you're going to come to a point where you feel like everything's good, everything will work, and then you can move into the chassis. So the chassis should be the last part of design, pretty much just because it connects everything else. And it's really hard to connect things that don't exist yet, right? So if they're not there, if they're floating, if you know they're not well defined where they're going to be mounting, it's very hard. And I think the reason that the EV chassis is so big and not great is because a lot of stuff wasn't defined well when Oscar went and designed it. You know, suspension wasn't defined super well. We didn't have a battery pack layout yet. Kind of had motors, but we didn't know how we were going to reduce the power. And Oscar kind of took what he had and made a chassis before he graduated. So, you know, once everything's done, the chassis is not, you know, super difficult. Again, it's connecting points. There's a lot of rules that have to be met, but really, if everything falls into place, you know, this should be so well constrained that there's not a lot of room for, you know, different ideas. You know, you go connect everything, try to get as much mounting on the nodes as possible, and you'll have a good chassis. And, you know, Tim said this to me the other day, and I agree, that a good-looking car is well planned out, and a good-looking chassis is well planned out. And, you know, every good team designs this last. And it's hard because it's the biggest part of the car. You know, it takes the longest to make this single component than any other component. But you know, this is just this really just connects everything else together. Yep.
I think something to take from like a team like Wisconsin that I think we should definitely integrate into our you know, Sandy's been pushing it, but it's to model everything in the CAD, because it really helps with, like, it speeds up the assembly process. And when you do that, you know where every wire goes, how long each wire is, where all the washers go. There's no mistake about that.
Yeah.
But it does go a long way to come in terms of the organization.
Definitely.
To get to that point.
I mean, the more planned out you be, the better it's going to go, the faster it's going to go. And that's kind of true for anything, right? So again, like, there was some stuff that wasn't planned out super well in the IC car, and like bolts didn't fit right. And like didn't have clearance for heads of bolts, so we were like grooving dowel pins to like turn into pseudo bolts, and it was nuts, right? So the more you plan out, the more you have, modeled, clearance checking and all of that, the better your car is going to be. And that's more the direction the team needs to go, rather than like over-ambitious, design. Some more on the chassis. The chassis doesn't take priority over most aspects of the car, but it needs to be, considered. So, try to make things on like similar planes as other parts. You don't want to forget about it. The chassis is going to look pretty similar year to year, hopefully, and so you kind of know what to expect. Kind of make that. So again, understand the capabilities. So you don't want some crazy thing floating off in space that we're gonna have to go grab with tubes. You don't want a whole bunch of like really crazy bent bars. Designing the chassis also includes the impact attenuator, anti-intrusion plate, and the floor. And after all of that is done, then you move on to kind of finalizing the body aesthetics. At this point, it's probably pretty late, so I'm not suggesting you don't start designing the body until now, but you really can't finalize anything until everything else is done. The body is there to protect the driver from debris and to make the car look good. It shouldn't take precedent over any performance or engineering, especially a team like us that doesn't do aero. It's not structural, and it really can't hinder access to anything. And it's really the lowest priority part. So, just some final notes, some wisdom I kind of want to, wisdom/opinions I want to talk about. So aerodynamics in the future, moving forward, this isn't something you can just add to the car. It really changes a lot with suspension. As you saw, a lot of, it changes a lot with what your tires are. As we talked about earlier, that changes everything down the line. So this isn't something you can really just bolt onto a car after the fact. It's like, especially like when we're talking about like downforce aerodynamics. It's like pods to channel air and stuff like this. These are stuff that can be added, but once you change the downforce in the car, you can't just it has to be taken into account at the very beginning. So you need to know what your expected added forces are going to be at the beginning. And what it also does is really complicate suspension, because all the forces are no longer constant, they're all speed-based. So it basically makes any constant an equation, and obviously adding more degrees of freedom makes things a lot more complicated. If we're having trouble figuring out the basics, it's going to be tough when we add aero. The other thing is the carbon fiber monocoque. This is like, the way to go if you're a good team. There's just a lot of things that come with it. So we do our structural equivalency spreadsheet every year, and to do it for a monocoque requires that you do actual testing, physical testing. You have to send them samples, whole reports on tensile strength, compressive strength, bond strength. It's a lot to add. Another thing is you can't just weld on a tab. Everything has to be planned out. Anything that connects the chassis has to be there because you can't modify it after the fact. And with our steel frame chassis, something doesn't work, we forgot about something, we kind of just find a place for it, weld the tab on, bolt it on. It's not that big of a deal. For monocoque, that means game over. It means that design a new build a new monocoque, or just don't go to the competition. And then there's a lot of other interesting effects that carbon fiber has. So one example is my buddy is the powertrain lead at San Luis Obispo, and he was having a really, really hard time passing sound because of all the vibrations from the exhaust into the chassis. That's something that you don't consider, but they were like 5 decibels over, and they ended up having to use 2 mufflers and crazy stuff just to pass the sound. And so there's a lot going down any ambitious design goal, or is going to be those black boxes you don't even consider, and they can really throw a wrench in your plans. So I think that's it. Does anyone have any questions? Yeah.
I'm a little new to this, but when you guys are designing, like you said before, how you design everything final in a model, or CAD, SolidWorks, whatever else,
Yep.
whatever other program you guys use, do you guys do finalized numbers, and then from there move on to the next stage and the next stage? Because what I was thinking when you said aerodynamics, where you said it isn't something you can just add, the first thing that popped in my mind is to use variables all throughout the entire design, taking into account possible things that you can't be using, and then aerodynamics would kind of be some final variable that you input, and everything else changes according to that.
Yeah, so it's hard. There's a lot of, theoretically, I suppose you could design the whole car in variables and, adjust one and see how it affects the whole rest. But there's also a lot of practical things that, this material needs to be here, it's not taking any force, that it would be hard to do that for. And also, aerodynamics specifically is very hard to get accurate in the virtual world. So when I talk about knowing the exact force, that's building models, testing it, kind of stuff. Because if you're off and again, your suspension's not going to work, your car's going to handle horrible, and it's just something that I hear get talked about a lot, but it's not something I feel like we're ready for, especially because we don't have static suspension variables figured out well, let alone making them dynamic. Any other questions? All right. Thanks, guys.